All right, guys, so this is the Unit 4 problem review answer set. So the answers are online, and I'm just talking you through what I did questions. So in the first one, it gives you some information about the simple harmonic oscillator. So there's a mass of 0.8 kilograms, spring constant of 49.4 newtons per meter, and the amplitude of the motion is 0.6 meters. So I always like to draw a sketch here to kind of get a feel for what's going on. So I'm starting with it at its positive amplitude. And then we're going to keep set the thing in motion and let it oscillate. So I first let go, its velocity is 0, and then the spring pulls it towards equilibrium. It keeps moving through the equilibrium, and it compresses it, and then it's oscillating back. So that's one complete cycle. Part A asks for the frequency of the oscillation. So the first thing I did was calculate the period. So I just plugged in the 2 pi squared of m over k. I got the period to be 0.8, and then you take the inverse of the period to get the frequency. So 1.25 hertz is the frequency of the oscillation. For part B, it asks for the 3 equations of motion. So that's referring to position as a function of time, velocity as a function of time, and acceleration as a function of time. So I just plugged in the amplitude value again was 0.6. I solved for omega using that. So omega turns out to be 7.85. And then I just did the formulas that are on the equation sheet to figure out the position as a function of time, velocity as a function of time, and acceleration as a function of time. So these are the answers for those over here, plugged in and solved. C asked you to evaluate the position when it's at 3.7 seconds. So time is equal to 3.7 seconds. So when I did that, I got 0.6 cosine of 7.85, which is omega, times the time that we're evaluating at is 3.7. Make sure you're in radian mode. That's really important. And I got negative 0.43. So it's to the left of the equilibrium position, and it's not quite at the amplitude, which is 0.6. Finally, it asks you to evaluate and solve for the potential and kinetic energies at that time. So the potential energy, I just used the location, so 1/2 kx squared. I used the location that we just got in part C. I squared it, multiplied it by k and a half, and I got 4.58 joules. To find the kinetic energy, I could have done it a couple different ways, but I just evaluated the velocity function at 3.7, and I got 3.7 or 3.27 meters per second for that velocity. And then I just squared that number and multiplied it by 0.8 times a half. So 4.29 joules kinetic energy. If you add those together, that would get you your total energy. And that was pretty close. He asked you to graph out 2 functions of the oscillation, or 2 periods. So these are the 2 periods. So it started at a maximum, and it goes back to a maximum. That's 1 period. So it's the same kind of idea. We said the period was 0.8, so you divide that in half to get halfway through, which is 0.4. We divide it into quarters, that would be those values. So we repeat that, and it's oscillating through that. So then it asked you to kind of discuss what was happening at 3.7 seconds. So describe the motion at 3.7. So if we wanted to figure out how many times we've oscillated at that point, we could take 3.7 and divide by 0.8. So that's what I did. So it's 4.625 oscillations is what we've done. So we've gone 1 time, 2 times, it would repeat 3, 4, and then we're at this 0.65. So 0.65 is like a little bit past halfway, but not all the way to 3/4. So I put an asterisk here because that's about where 0.625 of an oscillation is. 0.625 times 8 or 0.8 would be 0.55. So 0.55 is somewhere kind of in here where I put the asterisk. And I'm just looking at what's happening there. So I have a negative position. I've already evaluated that, got that value. So I'm at a negative location, which is good for my graph. That's where I'm at. The velocity is the slope of that. So I can plug into that. I got the velocity to be positive 3.27. So when that happened, that means I have a positive slope here. The slope of position versus time graph is the velocity. And if you think about it, it's speeding up because it goes its maximum speed when it gets back to the equilibrium, or x equal to 0, which is this x-axis going across. So it's going from 3.7 or 3.27 up to the maximum speed there. So it's speeding up. So I said it's speeding up and moving right, which is maxing or describing the motion of that. So that was number 1. For number 2, it's a pendulum situation. So they want you to find the acceleration due to gravity, which is just little g. And they want you to do that when the length of the period was 0.75 meters or 75 centimeters, and they tell you at a very exact period value of 1.7357. So I went all my values to 4 places past the decimal point. So the equation for period is just 2 pi squared of L over G. We're going to solve for G first here. So I just plugged in and solved for G, and I got 9.8296. So this is not exactly kind of the average value that we use. It's a very specific value, but that's okay. So that's the gravity that the pendulum is undergoing. Then it asks you to find what's the velocity when the pendulum reaches the bottom of the swing. So in that case, the potential energy that it starts with is changing into kinetic energy down here. So all the potential is changing into all kinetic. So so to do that, I just use conservation of energy. So mgh equals 1/2 mv squared. And I didn't worry about the mass. It didn't tell me the mass. So I just canceled them out, or it might have told me the mass, but I didn't need it. I don't remember if I don't think I did. So the masses drop out. I solve for V, it's the square root of 2gh. I used gravity that we got here in part A, and the change in height or how far it fell was 0.07. So when I did that, I got the pendulum was moving at 1.173 meters per second. Then we're at the same location, but we have shrunk the length of the string. So we've shrunk the length of the string to some new length. So if we've decreased the L value, our new L is smaller than the original L, then we will also shrink our period because they're directly related. So if L gets smaller, T prime or the new period is going to get smaller. And the new period has decreased by 0.02 seconds, so it now is 1.7157. We're at the same location, so gravity is still the same, and we're going to solve for this new length. So I, again, just plugged into the period of a pendulum equation and solved, and I got the new length is 0.7329 meters. And that makes sense, right? So like originally we were 0.75, and if we make the length slightly smaller, the period will get slightly smaller. Okay, so that was the second one. The third problem is dealing with gravitation and force of gravity. So it's talking about between the Earth and the Moon. It tells you the values for the mass of the Earth, the mass of the Moon, and the separation between their centers of masses. So I just plugged into the universal gravity equation, big G m1 m2 over r squared, and I got this value. So 1.9975, you could have just said 2 times 10 to the 20th, that's fine. That's the force of gravity acting on the Moon from the Earth. It's also the force of gravity attracting the Earth towards the Moon. So those are fine. For part B, it's more talking about gravitational potential energy due to these two masses, so the Earth and the Moon. And we're trying to measure it at a location which I labeled X there in this picture. And there's a picture on your handout as well. So it says that this location X is the same distance away from the Earth that it is to the Moon. So the Earth and Moon were the 3.84 times 10 to the 8th distance apart. That was what we used in part A. And it's the same distance over here. So, so the distance from the Earth to location X is that value that we talked about before. The Moon is twice that distance away. So I doubled that to get the distance to the Moon. And then I just used the gravitational potential energy for this setup. So, so it's negative G m over r over r. So actually, look at this again. I just plugged into that equation, but I think I left this out. So that's not going to work. So because there is no potential energy there, we'd have to put a mass there. So I didn't put a mass. Let's just say the mass is 1, and that won't change the value any. So if the mass of this object is equal to 1, so this is a clarification on this problem, then if m is equal to 1 kilogram, then it would just be negative g, the mass of the Earth or the mass of the Moon, and then times 1 divided by the distance or separation between those objects. So for the Earth at position X, where X is equal to 1, it would be this value, negative 1,042,187.5. And for the potential energy between the mass of the moon and that 1 kilogram mass, it'd be negative 6,392.1. So those values together, if we wanted to find the total potential energy at that point acting on mass for the situation, you would just add them together. So you get negative 104,859.6. Might have left out a digit or two. Let me try to double check that because it looks different than what I think it should be. So 104,277.5 plus 6. Yeah, I left out a 7 here. I apologize for that. So so there's a couple problems with this problem, but I left out a 7 here. So 1,048,579.6 joules. That's the correct answer. So fixing that too. So I'll put a note on that on D2L. So I will see you guys next class.